Welcome to the PhotoModeler Vehicle Crush tutorial. In this tutorial, we will determine crush measurements on a vehicle using photographs taken from an unknown camera. To be able to do this project, you must have some known coordinate information for points on the uncrushed part of the vehicle. We can find this known information, or control points, from an identical exemplar, or undamaged vehicle. This exemplar vehicle is surveyed to extract 3D coordinates to be used as control points, which are needed by PhotoModeler's inverse camera to solve for the unknown camera parameters. This information could be measured using traditional survey instruments such as a total station. Or in this case, PhotoModeler with a calibrated camera was used as a surveying tool to extract the 3D coordinates from the exemplar vehicle. Any method that can generate an accurate set of 3D coordinates can be used as a source for control points. Here is a completed project done with a calibrated camera of an exemplar uncrushed vehicle. The project uses 6 photographs taken from a good variety of angles. The residuals are low and the project is solving well. Some measurement checks were done against the exemplar vehicle. This ensured a strong result and therefore a good set of control points, which in turn increases our chances of a good inverse camera result. We go to File, Exports, Export Model, and select 3D DXF. We turn on Point IDs and save the file as CorollaExemplar.dxf. Next, we start a new project to begin work with the photos of the crushed vehicle from an unknown camera. We choose a points-based project, browse to the folder with our images, and add them to the project. Since we do not know anything about the camera that took these crushed photos, we choose an unknown camera solved by control points. We click Next and get a pop-up telling us that an inverse camera description cannot be shared by 2 photographs. Since we do not know anything about the photos, we could not assume that they were taken by the same camera or at the same focal length settings. This message tells us that a copy of the camera has been made. We now have 2 cameras in the project, each assigned to a separate photograph, allowing them to be solved for independently. The message also tells us the focal length flag has been set. This means that the focal length option in the photo properties is set to be solved when inverse camera processes. In certain cases, you may want to solve for the principal point as well as the focal length. This may be necessary if you think the photographs have been cropped and the image is off-center. Solving for principal point requires a very strong set of control points, and you should try solving for just the focal length first. The format aspect ratio is not often solved in inverse camera and only solved for it if you suspect there is a scanner error or some other problem that would affect the squareness of the pixels. To set these or other parameters for solving in inverse camera, use the Photo Properties dialog. When working with photos from an unknown camera, something needs to be known about the scene, so PhotoModeler can back-calculate information about the camera. In this case, we will use known 3D X, Y, Z locations imported as control points. To add the control points, we open up the Import Explorer and select Add Imported Object. We select the CorollaExemplar.dxf file we exported from our exemplar vehicle project. The units for this file are inches. And we choose Fixed to ensure that the control point coordinates are not adjusted during processing. This is suitable when you will mark a low number of control points. Since we included point IDs with our export, we will turn on text fields for point names. Click OK. The project units are set to inches. You can see that we have a fairly detailed model of the undamaged exemplar Toyota Corolla. This model actually contains more detail than is normally required for a control point project, but this detail will help demonstrate aspects of this project later in this tutorial. We click the List View tab. If we scroll the list, we see that all the points have ID numbers. There is also a name column. The ID numbers are sequential numbers for the points as they come in from the file. The name field comes from text entities in the DXF file. In this case, the numbers are the point IDs from the exemplar project. If we had used the renumber command before exporting, the two IDs would match up. You can see some ID names have text describing the point. These particular points have been named to help us identify the points more easily when we mark the control points on the photos. For example, this point, point 107 in the exemplar project, is named ds.frontrail, which is short for the front part of the rail molding that runs down the driver's side of the car. We select the front rail point. If we switch back to the 3D view, you can see the front rail point is highlighted in red. You can select points in either the 3D or the list view. We open Photo 1, where this point is displayed. We'll switch to Import Marking mode and move over Photo 1. The cursor switches to the Import Marking display, and we use Alt-Zoom to take a closer look and mark this point. Next, we will mark this point. Here, followed by this one, here. Incorrect or inaccurate control point marking will give poor results in inverse camera processes. We need to make sure we mark our points accurately. We next mark this point. It is very important that the control points have good coverage on the photo. You want to try and have control points marked across the photo rather than all bunched in one area. Especially when solving for focal length, you should have some points with varying depth, otherwise you may get poor results, or inverse camera may not solve at all. All our points so far are covering this one plane of the driver's side. This point, passenger side, C-pillar bottom window, represents a point on the other side of the car. This can be viewed through the windows. We now have some depth coverage of the photo. Enough points have been marked for the project to process. The camera's position and inverse camera focal length have been solved. This processing has been done using the minimum number of points. If the points marked did not have sufficient spread across the photo, you may get an orientation failed message. In this case, you should confirm the points marked are correct, and you may need to mark some more points to strengthen the project before the orientation will succeed. Here on Photo 1, we have marked some additional control points on undamaged parts of the vehicle to strengthen the project solution. We have reviewed our marked locations and checked the residuals to make sure the project is solving relatively well. Another check we can do to ensure the project is solving correctly is to turn on the 3D projected model and check that it lines up with the photos. Go to Visibility, turn on Imported Points and Lines. Here we can see overlying the photo the lines from the imported control file. We can change the settings to make them more solid so they're easier to see. We study the photo to see how well the control file matches the vehicle in the photo. The marked control points have been used to lock the rest of the control file in place. Of course, the projected lines on the front area will not match the crushed area in the photo, but the uncrushed area should match correctly. We check how well the lines match up along the windshield, windows, and doors. Everything seems to line up well. We will turn off 3D display and open a point table quality. Our review of the marked placement improved our residuals. In an inverse camera, project residuals can be judged differently. In this project, we are solving for the camera parameters using control points that are set so that their coordinates cannot be adjusted and we are not 100% sure they are marked in the correct position. This results in higher points residuals. For these types of projects, residuals around 10 pixels are still acceptable, but lower would be better. When they start to hit 15 pixels and above, then you should review your control points to see if they are positioned correctly. The residuals in this project are acceptable, so we close the point table. We can now mark control points on Photo 2. Close Photo 1 and open Photo 2. Switch to control point marking mode. Again, we start with points which are easy to mark and have a good spread across the photo. Start with this point here. Followed by this point here. This point we can see through the window here. This one we can also see through the window here. To make sure we have a good spread across the photo, mark this point here. The minimum number of points has been met and Photo 2 is now oriented. We will mark some additional control points to strengthen Photo 2. Here we have Photo 1 and 2 marked with a good set of control points. We have reviewed the residuals of the project and things are solving well. We will demonstrate a technique that can be used to verify the project solution. We switch to referencing mode. We mark a point at the cross of this T. We move our cursor to the other photo, which becomes the destination window. The reference helper line, also called the epipolar line, appears. We can see that this line goes through the section we marked. The reference helper line helps us find the intersection where we should mark the matching point. We mark the point at this intersection. We will try with another point. We mark the intersection of the T on the window here. Go over to our destination and see if the reference helper line matches up. If the reference helper line appears off target, such as up here, this is an indicator that the project results are not ideal. If this was the case, we would have to review the placement of our control points and ensure we have sufficient control points with good coverage across the photo. Reference this point here. If your project has large residuals and the projections or reference helper line is not lining up, check your control point placement. You should also be sure that the exemplar vehicle that you got the control points from is the exact same model vehicle. It should be the same make, year, and model. Even some minor features such as body lines and molding can vary in shape or location in the same models due to dealer options and production variations. Similarly, with a road scene, you should be careful that features you are surveying for use as control points have not been moved since the time the original photos were taken. The survey of control points is usually done after the fact, and you want to be sure you are getting the coordinates for the objects that were in the same position at the time the original photos were taken. If we open a 3D viewer, we can see the imported control object as well as the points we have marked on the photos. Here are the 2 points we just added at the T intersections. To help identify which parts are from our imported exemplar vehicle, we will add a new material. We open the Materials dialog. Click Add and enter the name Exemplar Pink. And choose a pink RGB color for the material. Say OK. We now select a part of the imported control object and change the material for the object to Exemplar Pink. Our marked data is the default white, and our control data now shows in pink. We turn on camera stations and verify they are in appropriate positions. We have performed our quality checks and are satisfied with our results. We can now move to the next step, which is marking and referencing of points on the damaged section of the car. Open both photos. Now the inverse camera photos are solved for. Using our control point data, we can continue with the project as normal. We hold down Control and left mouse drag to zoom in on the area around the crush. On photo 1 and on photo 2. Switch to Mark Points mode and mark some points on the crushed hood. Use Alt-Zoom to make sure the points are marked accurately. Mark some bolt holes and on parts of the bumper and undercarriage. We switch to Select mode and use Drag Region Select to select our newly marked points. We switch to Reference mode. Because points are selected, photo 2 has become the source. We move over to photo 1 and use the Epipolar Reference helper line to help reference selected points. Mark the points. Our final goal in this project is to get displacement measurements from a profile of the interior bumper shown here. The plastic covering of the bumper has fallen off, so we will use the inner bumper as our source for crush information. We use Image Enhance for a better view of this bumper in photo 2. There are not many distinct points to mark along the bumper. We'll mark a point along the top edge of the bumper near some other identifiable feature so we have a general idea of its location when comparing to the other photo. We then move the cursor to the other photo and use the reference helper line to find where it intersects the bumper near the feature here. We mark where the line intersects the bumper. Mark another point along the bottom of the bumper here. We do a quick check to make sure it's near the identifiable feature and mark where the bumper and epipolar line intersect. We mark some other points along the bumper close to where there are visual clues, if possible. Mark a point at the top of this scrape here, and where it intersects the bumper here near the scrape. We use the Line tool to connect the points, and we have created the initial profile of the bumper. The bumper has now been modeled in more detail, while some points have been added along the hood for a more complete model. We have a top-down view of the marked data and control lines. The pink lines represent the control file, while the white points and lines show the data we marked. The control file also shows this extra line that has been added to the level of the bumper. This line was added so we could do profile measurements. This extra line can be added to the DXF file using a CAD package or in a text editor in some cases. We hit Reset to go back to the top-down view. We zoom in on the camera on the front bumper. We want to get displacement measurements from this line to these bumper points. There are a couple of methods for doing this. You can do certain measurements right within PhotoModeler, or you can export the model to a CAD program. If you're using a technique where you want equally spaced measurements on your crush profile for doing your delta V calculations, it might be easier to export the crush project data to your CAD program in the form of a 2D DXF file. You can compare with a 2D DXF profile of the exemplar vehicle and do the equally spaced measurements within the CAD program, or even on a plotted drawing. To do the measurements in PhotoModeler, we open the Measure pane. Our scale was defined by the imported control points. We select the control line, press Shift, and select this point on the bumper. A distance of 17.57 inches is displayed in the Measure pane. This is a straight displacement measurement representing the closest distance between the point and the line. We do a few more displacement measurements between the bumper points and the control line. This concludes the crush measurement project using photos from unknown cameras. We are able to complete this project using the control points and inverse camera tools. We demonstrated how to import and view control data, mark control data to help solve the inverse camera, check the quality of the results, and do the measurements in PhotoModeler.